There are moments in the universe so energetic that they briefly outshine entire galaxies. Moments where space itself trembles, light is bent, and the quiet order of the cosmos is interrupted by something sudden, vast, and almost impossible to imagine. These events are not explosions in the ordinary sense. They leave no sound, no shockwave you could feel. And yet, for a few fleeting seconds, they can release more energy than our sun will produce over its entire lifetime. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like, a soft tap on subscribe, or simply staying with me through the night helps keep these calm explorations alive more than you know. Thank you for sharing this stillness with me. Now, we drift gently into the first part. Part 1. What existed before atoms? Before the first atom could ever take shape, the universe was a place without structure, no chemistry, no solids, no light traveling freely through space. There was only an intense, searing sea of energy, so hot and dense that nothing could stay together for long. Protons and electrons existed, but they could not touch. The universe itself was too restless, expanding too fast, vibrating too violently. To understand the first atom, you must first imagine a cosmos where connection was impossible, where even the idea of matter had not yet settled into form. If you could drift backward in time, not in years but in fractions of seconds, you would find yourself in a universe that feels less like space and more like motion itself. Temperature was not just high, it was defining. Energy ruled everything. At this stage, the universe was measured not by distance but by change. Every point of space was filled with particles colliding, separating, transforming, too energetic to pause, too crowded to organize. In the earliest moments after the Big Bang, the universe was smaller than a grain of sand, yet heavier than all the galaxies combined. This is not a metaphor. According to modern cosmology, all the matter and energy we observe today was compressed into a region so dense that our current laws of physics struggle to describe it. Space and time themselves were tightly bound together, curving and shifting under the pressure of unimaginable energy. As the universe expanded, it began to cool, not quickly by human standards, but inexorably. Cooling in the universe does not mean losing heat to something else. There was nothing else. Cooling meant expansion, energy spreading out, becoming less concentrated. And with that slow cooling came the first opportunities for structure. But structure did not arrive all at once. For the first tiny fraction of a second, known as the Planck era, even the fundamental forces of nature were unified. Gravity, electromagnetism, and the nuclear forces were indistinguishable from one another. The universe did not yet know how to behave as separate interactions. Everything was governed by a single incomprehensible rule, one we have not yet fully uncovered. As time moved forward, if that word even applies at such scales, symmetry began to break. Forces separated. The universe chose distinctions. Gravity peeled away first, followed by the strong nuclear force, and later the electromagnetic and weak nuclear forces. These separations were not gentle. They reshaped reality itself, defining how particles would interact for the rest of cosmic history. Only after these distinctions formed could particles as we recognize them begin to exist. Quarks emerged first, fundamental building blocks that would later form protons and neutrons. But even quarks could not remain bound for long. The universe was still too hot, too energetic. Quarks collided and separated in a constant churn, a dense plasma where nothing stayed together long enough to become familiar. As expansion continued, quarks finally began to settle into more stable arrangements. 3 quarks bound together became protons and neutrons. This moment, occurring within the first second of cosmic time, marked the first appearance of particles that would one day anchor matter itself. Yet even now, atoms were still impossibly far away. The universe was filled with protons and neutrons, along with electrons and a flood of high-energy photons. Light existed, but it could not travel freely. Every photon was immediately scattered by charged particles. The universe was opaque, glowing, more like the interior of a star than the vast darkness we know today. During the first few minutes, a brief window opened for nuclear fusion. Protons and neutrons combined to form the nuclei of hydrogen, helium, and trace amounts of lithium. This period, called Big Bang nucleosynthesis, set the elemental foundation of the universe. Nearly all the hydrogen you breathe today was forged in these first minutes. But nuclei are not atoms. An atom requires electrons to bind to a nucleus, forming a stable neutral structure, and for that to happen, the universe needed to cool much further. Electrons, light, and nuclei could not yet coexist peacefully. Every attempt at connection was immediately undone by energy. For hundreds of thousands of years, the universe remained in this charged state. Electrons raced freely, photons bounced endlessly, space glowed with a uniform brilliance, a hot fog of radiation and particles locked together. If you had been there, there would have been no darkness, no transparency, no stars or shadows, just a constant blinding brightness with no direction, no distance, no night. Then, quietly, without any explosion or announcement, something remarkable happened. The universe cooled just enough. At around 380,000 years after the Big Bang, temperatures dropped to roughly 3,000 degrees Kelvin, still hotter than most stars' surfaces, but calm enough for a new kind of stability. Electrons slowed, nuclei held steady, and for the first time, electrons could attach themselves to protons without being immediately torn away. The first atoms formed. This moment is called recombination, though it was really a first combination. Hydrogen atoms emerged, simple and delicate, each one a proton holding onto an electron in a fragile balance, defined by electromagnetic attraction. With atoms finally neutral, photons were released from their endless scattering. Light could travel freely for the first time. The universe became transparent. That ancient light still exists. It has been stretched by billions of years of expansion, cooled from visible brightness to faint microwaves. Today we detect it as the cosmic microwave background, a soft, uniform glow filling the sky in every direction. It is the afterimage of the moment atoms were born, a photograph of the universe taking its first clear breath. Before atoms, there was no chemistry, no molecules, no solids, liquids, or gases. There was no way for complexity to emerge. Atoms were the quiet turning point, the moment the universe shifted from chaos to possibility. And yet, even after atoms formed, the universe was still dark. There were no stars yet, no galaxies. Gravity had begun its long, patient work, pulling atoms together over millions of years. Tiny variations in density, seeded in the earliest moments, slowly grew. Regions slightly denser than average attracted more matter. The process was slow, silent, and inevitable. Everything familiar, stars, planets, life, rests on this sequence of cooling, separation, and connection. Atoms were not inevitable. They were permitted by timing, by balance, by a universe expanding at just the right rate. If expansion had been slightly faster, matter would have thinned too quickly. Slightly slower, and the universe might have collapsed back into itself. The existence of atoms depends on this delicate edge between extremes. As you rest here now, breathing air made of atoms billions of years old, it's worth lingering on that thought. There was a time when nothing could hold together, when even the simplest connection was impossible. Atoms are not basic, they are earned. They are the universe choosing stability after chaos, structure after motion, quiet bonds after unimaginable heat. And from those first atoms, everything else slowly followed. As we continue this calm journey backward through the early universe, one question gently waits ahead. If atoms needed the universe to cool and expand to exist, what kinds of energy could still unleash destruction on a scale that rivals those earliest moments? Part 2. How hot was the early universe really? In its earliest moments, the universe was hotter than the core of any star that would ever exist. Temperatures exceeded billions of degrees, and energy ruled completely over matter. At these extremes, particles collided endlessly, breaking apart as quickly as they formed. Nothing could remain intact. The universe was young, but it was already vast, stretching outward in all directions, cooling slowly, patiently, as time began to take its first measured steps forward. To understand this heat, it helps to let go of everyday comparisons. Even the hottest stars we know, with cores reaching tens of millions of degrees, are cool by early universe standards. In the first second after the Big Bang, temperatures climbed into the trillions of degrees. At that level, heat was not just a condition, it was the defining feature of reality itself. Heat in physics is motion. The faster particles move, the hotter something is. In the early universe, motion was relentless. Particles did not drift. They slammed into one another at near-light speeds, exchanging energy so rapidly that no structure could survive. Any attempt at forming a stable configuration was immediately undone by another collision. At these temperatures, matter behaved in ways that feel unfamiliar. Atoms could not exist. Nuclei could not exist. Even protons and neutrons were unstable. Instead, the universe was filled with a quark-gluon plasma, a state of matter so extreme that it is rarely found today outside of particle accelerators. Quarks, the fundamental constituents of protons and neutrons, moved freely, unbound by the strong force that would later lock them into place. This was not chaos without rules. Even here, physics operated with quiet precision. The same equations that describe particles in modern laboratories applied then, just under far more intense conditions. The difference was scale. Everything happened everywhere at once. As the universe expanded, its temperature fell. This cooling was not dramatic or sudden, it was steady, smooth, governed by expansion itself. When space stretches, energy spreads out. Photons lose energy as their wavelengths lengthen. Motion slows, temperature drops. Within the first microsecond, the universe cooled enough for quarks to bind together. Protons and neutrons formed not as permanent residents, but as temporary islands of stability in a sea of energy. Even then, they were constantly being created and destroyed, appearing and vanishing as collisions continued. By the time the universe was 1 second old, temperatures had dropped to around 10 billion degrees. That still sounds unimaginably hot, and it was. But this change mattered. It marked the transition from a universe dominated by pure radiation to one where matter could begin to play a lasting role. At around 3 minutes, another threshold was crossed. Nuclear fusion became possible, briefly. Protons and neutrons fused into the nuclei of hydrogen and helium. This process did not last long. The universe cooled too quickly for heavier elements to form. When fusion stopped, the elemental makeup of the cosmos was set for hundreds of millions of years. Throughout all of this, light was trapped. Photons filled the universe, but they could not travel freely. Every photon collided with an electron almost immediately. The universe was like a dense fog of light and charged particles, glowing intensely, but offering no visibility, no distance, no darkness. If you imagine the interior of the sun, where light can take thousands of years to reach the surface, you begin to approach this idea. But even that comparison falls short. Temperature, at this stage, was uniform to an extraordinary degree. Wherever you looked, the universe was almost exactly the same temperature. Variations existed, but they were tiny, 1 part in 100,000. Those tiny differences would one day matter greatly. But for now, the universe was smooth, hot, and remarkably even. As expansion continued, the temperature dropped into the millions of degrees, then hundreds of thousands. Protons and electrons still could not combine. Any attempt to form an atom was instantly reversed by energetic photons. The universe remained ionized, electrically charged throughout. This era lasted far longer than the violent opening moments. For hundreds of thousands of years, the universe cooled in near silence, glowing steadily, expanding patiently. Nothing dramatic happened, no explosions, no sudden changes, just the slow march of temperature downward. Then, at around 380,000 years, the universe crossed a quiet boundary. Temperatures fell to about 3,000 degrees. That number may still sound extreme, but it marked a turning point. At this temperature, photons no longer carried enough energy to rip electrons away from nuclei. For the first time, atoms could survive. This was not a flash or a bang, it was a gradual settling. Electrons slowed, nuclei held firm, and neutral atoms formed across the cosmos. As soon as this happened, Photons were released from their endless scattering. Light began to travel freely. The universe went from opaque to transparent. That transition marks one of the most important moments in cosmic history. The light released then has been traveling ever since, stretched by expansion, cooled from visible brightness to a faint microwave glow. It still surrounds you now, arriving evenly from every direction, a whisper from a time when the universe first became calm enough to let light move unimpeded. When scientists say the early universe was hot, they mean more than high temperature. They mean a reality defined by energy rather than structure. Matter existed only in fleeting forms. Stability was temporary. Everything was in flux. And yet, this heat was not destructive in the way we imagine fire or explosions. It was creative, permissive, setting the stage for everything that followed. Without this extreme heat, the universe would not have evolved as it did. The early fire ensured uniformity, erased irregularities, and allowed small fluctuations to grow gently over time. As the universe cooled further, gravity began to assert itself more strongly. Atoms clumped. Regions slightly denser than average pulled in more matter. Millions of years later, the first stars ignited, bringing localized heat back into a universe that had grown dark and cold. But those later fires were small compared to the original heat of creation. The early universe reminds us that temperature is not just a number. It is a measure of possibility. When things are too hot, nothing can hold together. When things are too cold, nothing can change. Life, structure, and complexity live in the narrow window between extremes. You exist because the universe cooled at just the right pace. As you rest now, in a world warmed gently by a stable star, it's easy to forget that heat once filled all of space equally, that there was a time when nowhere was calm, when energy ruled without exception. The universe learned to cool. And in doing so, it learned how to build. As we continue this quiet exploration, another question begins to form. If the early universe held so much energy, where did it all go? And could such concentrated power ever appear again? Part 3. Why couldn't electrons attach to nuclei at first? Even though protons and electrons were present, they lived separate lives. The energy filling space was so intense that any attempt at bonding was instantly torn apart. An electron drawn toward a proton would be knocked away by a passing photon almost immediately. The universe was bright, opaque, and turbulent. Light itself could not travel freely. Everything was constantly interacting, colliding, and dissolving again into motion. To understand why electrons could not settle into orbit around nuclei, it helps to think not in terms of objects, but in terms of energy balance. In the early universe, energy was everywhere. Not stored neatly inside particles, but moving freely as radiation. Photons flooded all of space, carrying enormous amounts of energy, far more than they do today. An atom forms when an electron becomes bound to a nucleus by the electromagnetic force. This bond has a specific strength, a precise amount of energy known as the binding energy. For hydrogen, the simplest atom, that energy is about 13.6 electron volts. As long as the surrounding environment carries more energy than this, atoms cannot survive. In the early universe, photons routinely carried energies many times higher than that threshold. So when an electron drifted near a proton, drawn in by electric attraction, the bond did not have time to stabilize. Almost instantly, a photon would strike the electron or the atom itself, delivering enough energy to rip the electron away. This process is called ionization, and in the early universe, it happened continuously, everywhere, without pause. The result was a fully ionized plasma. Plasma is often called the fourth state of matter. It is neither solid, liquid, nor gas. It is a sea of charged particles where electrons roam freely and nuclei exist without their usual companions. Today, plasma exists in lightning, auroras, and the interiors of stars. But in the early universe, plasma was not a special state, it was the default. Everywhere you looked, protons and electrons moved independently, responding instantly to electromagnetic forces. Light could not pass through this plasma easily. Photons scattered endlessly, bouncing from particle to particle, changing direction so frequently that no clear path could form. This scattering is known as Thomson scattering, and it defined the universe for hundreds of thousands of years. A photon might travel only a tiny fraction of a second before colliding with an electron. There was no concept of visibility, no distant light sources, no darkness. The universe glowed uniformly, but nothing could be seen. If you imagine standing inside a dense fog where every step forward is met with resistance, you begin to approach the idea. But this fog was made of light itself. The inability of electrons to attach to nuclei was not a failure of attraction. Electromagnetism was already fully active. The issue was competition. The universe was simply too energetic for stability. Bonding requires calm. It requires that forces be allowed to act longer than the disturbances around them. At this stage, disturbances were constant. Temperature, which is really a measure of average particle energy, was the deciding factor. As long as temperatures remained above a few thousand degrees, photons retained enough energy to disrupt atomic bonds. The universe had to cool far more before atoms could persist. Cooling, again, did not mean heat flowing away. There was nowhere for heat to go. Cooling meant expansion. As space stretched, photon wavelengths stretched with it. Energy diluted. Photons lost their bite. But this took time. For nearly 380,000 years, the universe remained in this ionized state. That span of time may sound long, but on cosmic scales, it was brief. Still, during those centuries of thousands of years, the universe changed slowly and quietly. Electrons continued to scatter light. Nuclei drifted through radiation. Gravity began to subtly shape matter on the largest scales. Tiny differences in density, seeded in the earliest moments, persisted through this plasma era. Slightly denser regions tugged gently on their surroundings, gathering matter almost imperceptibly. Even before atoms formed, the blueprint of future galaxies was already being written. Eventually, the universe crossed a critical threshold. As expansion continued, temperatures dropped below about 3,000 degrees Kelvin. At this point, the average photon no longer carried enough energy to ionize hydrogen. Electrons could finally remain bound to protons without being immediately ejected. This transition did not happen everywhere at once. It unfolded gradually across space, but uniformly enough that the universe changed character almost everywhere within a relatively short cosmic window. This moment is known as recombination. The name suggests something returning, but in truth, atoms were forming for the first time. Electrons slowed just enough. Photons weakened just enough. Electromagnetic attraction finally had the upper hand. As electrons attached to nuclei, something else happened simultaneously. The universe became transparent. With fewer free electrons available to scatter photons, light was suddenly able to travel long distances without interruption. Photons that had been trapped since the beginning were released. Space, for the first time, allowed light to move freely. That release of light is still visible today. It has cooled dramatically, stretched by the expansion of the universe, and now appears as a faint microwave glow bathing all of space. This cosmic microwave background is not just evidence of recombination. It is a direct record of the moment electrons finally settled down. When scientists study this light, they see tiny temperature variations. These variations reflect the small density differences present at recombination, the same differences that would later grow into galaxies and clusters. In this way, the inability of electrons to bind early on indirectly shaped the structure of the universe. If electrons had attached earlier, the universe would have become transparent sooner. Structures would have evolved differently. If they had attached later, matter might have clumped too aggressively. The timing mattered. It always does. The early universe was not rushing. It was unfolding according to precise relationships between energy, expansion, and force. Electrons could not attach to nuclei not because something went wrong, but because the universe was not ready yet. Bonding is a low-energy activity. It requires patience. As you breathe now, electrons remain bound to nuclei around you. Atoms form molecules. Molecules form cells. All of this depends on a universe that cooled enough to allow stability. That stability was not guaranteed. There was a long era when nothing could stay together, when even the simplest atom was impossible. The universe had to grow quieter before it could grow complex. This story carries a gentle lesson. Complexity does not emerge from violence alone. It requires calm. It requires conditions to soften, energies to fall, interactions to slow. The early universe burned brightly, but it could not yet build. Only when the fire dimmed did structure appear. And as we continue this quiet journey through cosmic history, another question naturally follows. Once electrons finally attached and light was released, what did the universe look like in that first moment of clarity, when darkness and distance were born for the first time? Part 4. When did the universe finally cool enough for stability? As expansion continued, something gentle began to happen. Over hundreds of thousands of years, the universe cooled just enough for chaos to loosen its grip. Temperatures dropped below a critical threshold, not suddenly, not dramatically, but gradually. This cooling was not an event so much as a long exhale, and within that exhale, the conditions for stability quietly emerged. To understand this moment, it helps to let go of the idea that stability arrives with a sharp boundary. The universe does not flip switches, it drifts. Cooling was not a single instant marked by fireworks or sound. It was a slow crossing of many invisible lines, each defined by energy, motion, and probability. In the early universe, temperature and time were tightly linked. As space expanded, temperature fell. There was no thermostat, no guiding hand, just geometry. When the universe doubled in size, the energy density dropped. When it stretched again, photons lost more energy, their wavelengths lengthening as the fabric of space itself grew. For hundreds of thousands of years, this process continued quietly. Protons and electrons remained free, light remained trapped, and the universe stayed opaque. But beneath that apparent sameness, conditions were changing. The key to stability lies in competition. On one side was electromagnetic attraction, trying to pull electrons into orbit around nuclei. On the other was radiation, photons energetic enough to disrupt any bond that formed. As long as photons won that contest, stability was impossible. The universe could try again and again, but each attempt would fail. Eventually, expansion tipped the balance. At around 380,000 years after the Big Bang, the average temperature of the universe dropped to roughly 3,000 degrees Kelvin. This number is not arbitrary. It marks the point where most photons no longer carried enough energy to ionize hydrogen. Below this threshold, the electromagnetic bond could finally persist. Electrons began to settle. This settling did not happen all at once. Across vast regions of space, electrons attached to protons, forming neutral hydrogen atoms. Each successful bond slightly reduced the number of free electrons, and with fewer free electrons, photons scattered less often. This created a feedback loop. As more atoms formed, light traveled more freely. As light traveled more freely, the environment became calmer. As calm increased, atoms formed more easily. Within a relatively short cosmic interval, tens of thousands of years, the universe underwent a profound transformation. It became transparent. For the first time, light could move across vast distances without interruption. Darkness, as we understand it, became possible. So did distance. Before this moment, there was no way to see far because seeing itself required uninterrupted travel. This transition is often called recombination, but its deeper meaning is stabilization. It marks the universe's first lasting pause, the first time structures could survive longer than a moment. The light released during this transition still surrounds you now. It has been traveling for nearly 14 billion years, stretched and cooled by cosmic expansion. Today, it appears as a faint microwave glow, nearly uniform in every direction. This cosmic microwave background is not just ancient light, it is a snapshot of the universe at the moment stability arrived. When scientists study this background, they see tiny variations in temperature. These variations are small, but they are crucial. They represent the slight density differences present when atoms first formed. Those differences would later grow into galaxies, stars, and planets. In this way, stability did more than allow atoms to exist. It preserved information. Before transparency, photons constantly scattered, erasing fine details. After transparency, those details were frozen into the light itself. The universe gained memory. This period also marks a shift in what dominated cosmic behavior. Early on, radiation ruled. Photons carried most of the energy, dictating interactions. After recombination, matter began to take the lead. Gravity, slow and patient, could finally work more effectively without radiation pushing everything apart. But even then, stability was fragile. The universe was still simple. There were atoms, mostly hydrogen and helium, drifting through expanding space. There were no stars yet, no galaxies, no sources of new light. The cosmos entered a long era known as the cosmic dark ages. Darkness here does not mean absence of activity. It means absence of visible light sources. Gravity continued its quiet work. Slightly denser regions attracted more atoms. Over millions of years, clouds grew heavier, warmer, more concentrated. Stability did not mean stillness. It meant that change could now accumulate. Before cooling, every attempt at structure was erased. After cooling, small changes could persist and build upon one another. This is the essence of stability, not permanence, but continuity. From this point on, the universe could remember its past. Atoms survived, fluctuations survived, patterns survived long enough to matter. The cooling that allowed this was not dramatic, because drama requires contrast. In the early universe, everything was already extreme. There was no sudden silence after noise, no clear before and after. Just a slow easing, a gentle settling into a new regime of physics. If you imagine a lake after a storm, when the wind dies down and ripples slowly fade, you approach the feeling of this era. The water does not stop moving. It simply becomes calm enough to reflect. The universe reached a temperature where reflection, both literal and metaphorical, became possible. It is worth noting how narrow this window was. If the universe had cooled too quickly, matter would have clumped too early, creating a very different cosmos. If it had cooled too slowly, radiation would have dominated longer, preventing structure from forming efficiently. The timing mattered. Modern measurements show that the universe expanded at just the right rate to allow atoms to form, light to travel, and gravity to sculpt structure over billions of years. This balance was not planned, but it was precise. Stability emerged not because the universe sought it, but because the laws governing energy and expansion allowed it. As you rest now in a world defined by stable atoms and gentle temperatures, it can be soothing to remember that stability itself is a rare condition. It is not the default state of reality. It is something that emerges only when extremes soften. The universe did not begin as a place friendly to complexity. It became one slowly. That long exhale, spanning hundreds of thousands of years, laid the foundation for everything familiar. Every breath you take, every solid surface you touch, depends on that ancient cooling. And yet, stability is never permanent. Even now, the universe continues to expand and cool. Stars burn out, galaxies drift apart. In the far future, stability will take on new meanings, perhaps quieter ones. For now, though, the universe rests in a middle age, cool enough for atoms, warm enough for stars, calm enough for life. As we continue this quiet journey, another question gently waits ahead. Once stability arrived and darkness fell, how long did the universe remain silent before the first stars finally ignited and brought light back into the cosmos? Part 5. What exactly was the first atom? The first atom was simple. Just one proton and one electron, bound together by electromagnetism. Hydrogen, no complexity, no variety. Yet this simplicity carried immense consequence. For the first time, matter could remain intact. The universe had discovered how to hold itself together, even if only in the smallest possible way. Hydrogen is the most basic atom that can exist. It has no layers, no internal structure beyond a single positive charge and a single negative one, quietly balanced. And yet, this balance was something the universe had struggled to achieve for hundreds of thousands of years. When it finally happened, it changed everything that followed. To appreciate how profound this moment was, it helps to understand just how fragile an atom truly is. The bond between a proton and an electron is not rigid. It is a dynamic relationship governed by probability, motion, and force. The electron does not orbit like a tiny planet. It exists as a cloud of possibility, held close by attraction but never fixed in place. For most of the universe's early history, this delicate arrangement could not survive. Energy was too abundant, photons were too aggressive. Any attempt at bonding was undone almost instantly. Hydrogen, simple as it is, requires calm. When the universe finally cooled enough to allow hydrogen atoms to form, it did not suddenly fill with matter as we know it. Instead, space quietly populated with trillions upon trillions of identical atoms, each one nearly indistinguishable from the next. This uniformity is striking. There were no heavier atoms yet, no carbon, no oxygen, no iron, just hydrogen, with a small admixture of helium formed earlier during nuclear fusion. More than 90% of all atoms in the universe were hydrogen, and they would remain so for hundreds of millions of years. Hydrogen became the raw material of the cosmos. Each hydrogen atom carried within it the potential for everything else. But at this stage, potential was all it had. Hydrogen atoms drifted through expanding space, cold, dark, and largely uneventful. They did not glow. They did not clump easily. Gravity was weak on such small scales. Yet even here, something important had changed. For the first time, matter could persist. An atom could form and remain intact longer than a fleeting instant. That meant information could accumulate. Density differences could matter. Small variations could survive long enough to influence the future. The universe had crossed a threshold from constant erasure to quiet memory. Hydrogen atoms also marked the beginning of chemistry, though chemistry itself would wait much longer to unfold. Chemistry requires interactions between atoms sharing or exchanging electrons. In the early universe, atoms were too spread out and too cold for that. Still, the rules were now in place. The existence of hydrogen also allowed light to behave differently. Neutral hydrogen does not scatter photons the way free electrons do. With electrons bound to protons, light could travel farther, straighter, more cleanly. Space became transparent, and the universe entered its first truly dark era. This darkness was not empty. It was filled with hydrogen. Every region of space, no matter how vast, contained these simple atoms, drifting slowly, responding to gravity's quiet pull. Over time, slightly denser regions attracted more hydrogen. Gravity began its long work of amplification. Hydrogen's simplicity made it versatile. Because it is so light, hydrogen responds easily to gravity. It can collapse into clouds, compress, heat up, and eventually ignite. Every star that has ever existed began as hydrogen. Every heavier element was forged later, inside stars built from these first atoms. In that sense, hydrogen is not just the first atom, it is the ancestor of all atoms. Inside stars, hydrogen nuclei fuse to form helium, releasing energy that lights the cosmos. Later generations of stars fuse heavier elements, building the periodic table piece by piece. But none of that could begin until hydrogen existed as stable atoms. The first atom did not shine, it did not move dramatically, it did not announce itself, it simply stayed. That persistence was revolutionary. From a physics perspective, the formation of hydrogen represents a shift from plasma physics to atomic physics. Before hydrogen, interactions were dominated by charged particles and radiation. After hydrogen, neutral matter began to dominate large-scale behavior. This shift allowed gravity to become more effective. Radiation pressure weakened. Matter could clump without being constantly pushed apart by energetic photons. Structure could finally begin to grow. Hydrogen atoms also introduced a new scale of complexity, internal energy levels. An electron bound to a proton can occupy specific energy states. When it transitions between them, it absorbs or emits photons at precise wavelengths. This behavior would later allow scientists to map hydrogen throughout the universe, even across billions of light years. The famous 21-centimeter hydrogen line, for example, comes from a tiny change in the electron's orientation relative to the proton's spin. This faint signal allows astronomers to trace hydrogen clouds in galaxies and study the structure of the cosmos long after the first atoms formed. All of that information is encoded in the simplest atom imaginable. It's worth pausing here, because simplicity is often mistaken for insignificance. Hydrogen lacks the complexity we associate with life or technology. Yet without it, complexity itself would be impossible. The universe did not start with richness, it started with stability, and hydrogen was stable enough. As the universe expanded and cooled further, hydrogen atoms slowed. They began to gather under gravity, forming vast cold clouds stretching across thousands of light years. These clouds would eventually collapse, fragment, and ignite as the first stars. But for millions of years, nothing happened. This long pause after hydrogen's formation is sometimes overlooked. We imagine cosmic history as a sequence of dramatic events, but much of it is quiet. The first atom formed, and then the universe waited. That waiting mattered. It allowed gravity to work gently. It allowed fluctuations to grow without being erased. It allowed hydrogen to become the canvas upon which the rest of cosmic history would be painted. Even now, hydrogen remains everywhere. Most of the atoms in your body were once hydrogen in the early universe. Many were fused into heavier elements in stars, scattered by supernovae, and eventually assembled into planets and life. But their story began as that first simple bond between a proton and an electron. As you rest here now, surrounded by complexity, it can be calming to remember that everything traces back to something extraordinarily simple. One bond, one atom, one moment when the universe finally became quiet enough to hold itself together. And as we continue this slow journey forward through time, another question gently unfolds. Once the first atoms existed and the universe fell dark, how did gravity turn this simplicity into the blazing complexity of stars and galaxies? Part 6. How did recombination change the universe forever? This moment is known as recombination, though nothing was truly recombining for the first time. It was the universe's first successful attempt at neutrality. Electrons settled into stable orbits around nuclei, forming atoms that no longer scattered light endlessly. Space, once opaque, became transparent. Light was finally free to travel without constant interruption, carrying information across vast distances. Recombination marks one of the quietest turning points in cosmic history. There was no flash, no sound, no sudden wave sweeping across space. And yet, everything changed. The universe crossed from a state of constant interaction into one where separation, distance, and visibility became possible. Before this moment, light and matter were inseparable. Photons bounced endlessly between free electrons, never traveling far, never forming a clear path. The universe was bright, but it had no depth. There was no such thing as seeing far away, because far away had no meaning when light could not move freely. Recombination ended that confinement. As electrons bound to nuclei, the number of free charged particles dropped sharply. Photons, suddenly unimpeded, streamed outward in every direction. The universe did not grow brighter, it grew quieter. Radiation decoupled from matter. Light and substance went their separate ways. This separation is why the universe has a history at all. Once light could travel freely, it began to carry information. Every photon became a messenger, preserving a record of the conditions at the moment it was released. The temperature, density, and motion of matter were all imprinted into that light, frozen in place as the universe continued to expand. That ancient light still exists. Today, it reaches you as the cosmic microwave background, a faint glow detectable in every direction of the sky. It is remarkably uniform, yet not perfectly so. Tiny fluctuations in its temperature, differences of just millionths of a degree, reveal the earliest structure of the cosmos. Those fluctuations are not noise, they are the universe's fingerprints. They show where matter was slightly denser and where it was slightly thinner at the moment of recombination. Over billions of years, gravity amplified those differences, turning faint ripples into galaxies, clusters, and cosmic filaments stretching across unimaginable distances. Without recombination, this information would have been lost. Before transparency, photons scattered constantly, erasing detail. After transparency, the universe gained the ability to remember. Patterns could persist, causes could have lasting effects, history, in a meaningful sense, could begin. Recombination also marked a shift in cosmic dominance. Early on, radiation ruled the universe. Photons carried most of the energy and exerted pressure that resisted gravitational collapse. After recombination, radiation weakened as the universe expanded, while matter, now neutral and more stable, began to take control of large-scale behavior. Gravity, slow but relentless, finally had room to work. Atoms could drift together without being pushed apart by radiation pressure. Clouds of hydrogen grew denser over time. The universe entered a long, dark era where structure developed invisibly, guided by gravity alone. This darkness was not empty or lifeless. It was full of quiet motion. Hydrogen atoms gathered into vast regions, responding to tiny imbalances seeded long before recombination. Dark matter, already present and unaffected by radiation, provided scaffolding, deepening gravitational wells, and shaping where matter would collect. Recombination did not create stars, but it made stars possible. It allowed matter to cool further, to clump, to fall inward under its own weight. Millions of years later, the first stars ignited, ending the cosmic dark ages and reintroducing light, this time from concentrated sources rather than a uniform glow. But even then, the light from those first stars traveled through a universe already shaped by recombination. The transparency, established hundreds of thousands of years after the Big Bang, never went away. Space remained open, allowing light to cross billions of light years. In this way, recombination permanently altered the universe's character. It transformed space from a crowded, turbulent environment into an open arena. It introduced distance, perspective, and separation. It allowed the universe to be observed, not just experienced. From a human perspective, this moment also defines the farthest we can see. We cannot observe the universe directly before recombination using light, because light from earlier times could not travel freely. The cosmic microwave background represents a horizon, a limit beyond which the universe is hidden from view. To look earlier than that, scientists must rely on indirect clues, such as neutrinos or gravitational waves. Recombination set the boundary between the visible and the unknowable. It is the earliest photograph the universe has ever taken of itself. That photograph tells us something subtle and reassuring. The early universe was astonishingly uniform. Despite all its violence and heat, it smoothed itself out remarkably well. The differences that existed were small, controlled, and precisely the right size to grow into a structured cosmos. Had those differences been larger, gravity would have collapsed matter too quickly, forming black holes instead of galaxies. Had they been smaller, matter might never have clumped at all. Recombination preserved a balance already in place. This balance is not coincidence. It is the outcome of physical laws acting consistently across all of space. As you rest now, surrounded by a universe filled with light from distant stars and galaxies, it can be calming to remember that visibility itself is a gift of this ancient transition. Every image captured by a telescope, every glimmer in the night sky, depends on that first moment when light was set free. Recombination did not just change what the universe was made of, it changed how the universe could be known. It turned space into a medium for communication. It allowed the cosmos to tell its story across time. Even the largest explosions we study today, gamma-ray bursts, supernovae, violent mergers, are only visible because recombination happened first. Without transparency, their light would never reach us. In that sense, recombination quietly underlies all cosmic drama. It is the calm that made observation possible, the stillness that allowed motion to be seen. And yet, it is easy to overlook because it lacks spectacle. There is no singular image of recombination, no bright flare to point to. Its power lies in its subtlety. The universe did not become stable all at once, but it became legible. As we continue this gentle journey forward through time, another question naturally emerges. Once light was free and matter could clump, how did gravity transform a dark, simple universe into one filled with stars, galaxies, and eventually, worlds like our own? Part 7. Why did light suddenly decouple from matter? Before atoms formed, light and matter were locked together, endlessly exchanging energy. But once electrons found stable homes around nuclei, photons were released from that grip. They streamed outward in all directions, untouched, uninterrupted. That ancient light still exists today, stretched thin by expansion, now observed as the cosmic microwave background. It is the oldest light you can ever see. To understand why this decoupling happened, it helps to imagine the universe before it occurred as a crowded room with no silence. Photons filled every space between particles, constantly colliding, scattering, transferring energy. Light could not move freely because there was always something in its way. Every electron acted like a barrier, every charged particle like a mirror. Light, in this early era, did not illuminate, it interacted. Photons carried enormous energy, enough to keep electrons from settling down. And electrons, being free and abundant, ensured that photons could not travel more than a tiny distance before being deflected again. This mutual grip between light and matter defined the universe's first hundreds of thousands of years. Then, quietly, the conditions changed. As the universe expanded, photon energies dropped, their wavelength stretched with space itself, reducing their ability to disturb atomic bonds. At the same time, electrons slowed, losing the frantic motion imposed by extreme heat. When electrons finally bound to nuclei, they stopped behaving like loose obstacles scattered everywhere. This changed everything for light. A neutral atom does not interact with photons the same way a free electron does. Once electrons were bound, the probability that a photon would scatter dropped dramatically. Space went from being a dense fog to something closer to open air. Light decoupled from matter not because light changed, but because matter did. This moment is often described as photons being released, but nothing physically pushed them away. There was no forceful separation. It was more like a door quietly opening after a long wait. Photons that had been trapped simply continued moving in whatever direction they were already headed, now unimpeded. From that instant on, those photons traveled freely through the expanding universe. Some would eventually encounter newly formed stars or galaxies and be absorbed or scattered again. But many would never interact with matter at all. They would drift for billions of years, cooling, stretching, carrying. With them, a snapshot of the universe at the moment of decoupling. That snapshot is remarkably precise. When we observe the cosmic microwave background today, we are seeing light that last interacted with matter when the universe was about 380,000 years old. At that time, space was filled with newly formed hydrogen atoms, and the universe had a temperature of around 3,000 degrees Kelvin. As the universe expanded, that light cooled along with it. Today, it has a temperature of just 2.7 degrees above absolute zero. It is faint, invisible to human eyes, detectable only with sensitive instruments, and yet it is everywhere. No matter where you look in the sky, you see it. This universality tells us something profound. Light decoupled everywhere at nearly the same time. The universe transitioned from opaque to transparent almost uniformly. This reveals how smooth and consistent the early cosmos was on the largest scales. But the cosmic microwave background is not perfectly smooth. Tiny variations in temperature, 1 part in 100,000, ripple across it. These variations correspond to slight differences in density and motion at the time of decoupling. They are the seeds from which all later structure grew. Without decoupling, those seeds would have been erased. As long as light and matter were coupled, radiation pressure smoothed out irregularities. Photons pushed against matter, resisting gravitational collapse. Once decoupling occurred, that pressure weakened. Matter was free to follow gravity's slow pull without constant interference. In this way, decoupling allowed gravity to begin shaping the universe more decisively. It also marked the end of the universe's first phase of visibility. Before decoupling, the universe glowed intensely but could not be seen through. After decoupling, it became transparent, but also dark. There were no stars yet, no galaxies, just drifting atoms and ancient light moving silently through space. This era is sometimes called the beginning of the cosmic dark ages. Darkness here does not imply emptiness or inactivity. It simply means the absence of new light sources. The only light present was the fading afterglow of the Big Bang itself. That afterglow tells us not just about temperature, but about motion. Subtle patterns in the cosmic microwave background reveal how matter was moving at the time of decoupling. Some regions were slightly hotter or cooler due to tiny velocity differences. These motions would later influence how matter clustered. Light, once freed, became a messenger of all these details. This is why decoupling is so important to cosmology. It is the earliest moment we can directly observe using electromagnetic radiation. Everything before it is hidden behind a wall of opacity. The universe, before decoupling, is real, but invisible to light. To peer earlier, scientists must use other messengers, like neutrinos or gravitational waves, which interact far less with matter. But light itself can only tell the story from this moment onward. In that sense, decoupling is the universe's first act of communication. It allowed information to travel across space and time. It allowed regions of the universe to become causally aware of one another over vast distances. It allowed observation, memory, and eventually understanding. Every image of a distant galaxy, every spectrum of a star, every burst of high-energy radiation we detect today depends on this ancient transition. Light can only reach us because it was once set free. Even the most violent events in the universe, supernovae, black hole mergers, gamma-ray bursts, announce themselves through light traveling across transparent space. That transparency traces back to decoupling. There is something quietly comforting about this. The universe did not begin by shouting. It began by letting go. Light did not need to be forced outward. It simply waited for the universe to become calm enough to allow passage. Once that calm arrived, light carried the universe's story forward, uninterrupted, patient, enduring. As you rest now, surrounded by light from lamps, screens, and distant stars, it is easy to forget how rare visibility truly is. There was a time when nothing could be seen, when light itself was trapped. That time ended not with drama, but with balance. Light decoupled from matter because the universe finally allowed it to. And as we continue this gentle exploration, another question begins to glow softly ahead. Once light was free and darkness settled in, how long did the universe remain without stars, and what finally broke that long cosmic night? Part 8. How can we still observe the first atoms today? When you look at the cosmic microwave background, you're seeing a snapshot of the universe just after the first atoms formed. Tiny variations in temperature reveal slight differences in density, the earliest hints of structure. These faint patterns are not noise. They are the fingerprints of the first stable matter, preserved across nearly 14 billion years of cosmic history. It may seem almost impossible that something so ancient could still be visible at all. After all, the universe has been expanding for nearly 14 billion years. Galaxies have formed and collided. Stars have lived and died. Vast regions of space have grown cold and empty. And yet, the light released when the first atoms formed still reaches us, quietly, evenly, from every direction. The reason this is possible lies in the unique nature of that moment. When light decoupled from matter, it did so everywhere at once. There were no stars or galaxies yet, no localized sources of brightness. The entire universe glowed uniformly. When that light was released, it filled all of space, moving outward as space itself continued to expand. Those photons did not travel through space in the usual sense. They traveled with space. As the universe expanded, the fabric of space stretched, and the wavelengths of those photons stretched with it. What began as visible and infrared light slowly shifted to longer and longer wavelengths. Over billions of years, it cooled from thousands of degrees to just a few degrees above absolute zero. Today, that ancient light exists as microwave radiation. It is extremely faint, invisible to human eyes, but it is everywhere. No matter where you point a sensitive microwave detector, you will find it. This uniformity is one of the strongest pieces of evidence we have that the universe was once hot, dense, and nearly the same everywhere. But the cosmic microwave background is not perfectly smooth. Embedded within that faint glow are tiny temperature differences, on the order of 1 part in 100,000. These differences correspond to regions that were slightly denser or slightly less dense at the time the first atoms formed. Those differences matter. Denser regions contained a bit more matter and a bit more gravity. Over time, gravity amplified those tiny imbalances. What were once barely detectable ripples grew into clouds of gas, then galaxies, then clusters of galaxies connected by vast filaments of dark matter and gas. In this way, the cosmic microwave background is not just an image of the early universe. It is a map of everything that would come later. When scientists analyze this light, they are not simply measuring temperature. They are decoding information about the universe's composition, age, geometry, and history. The patterns in the cosmic microwave background reveal how much ordinary matter exists, how much dark matter shapes structure, and how dark energy influences expansion. All of that information is encoded in light released when the first atoms formed. The ability to observe this light depends on the universe remaining transparent. Once recombination occurred, space stayed mostly clear. There were no later events that filled the universe with free electrons again on a large scale. Stars and galaxies formed, but they did not ionize all of space at once. As a result, the ancient photons continued their journey largely undisturbed. They passed through the cosmic dark ages. They passed by the first stars as they ignited. They passed through forming galaxies and expanding voids. Some were scattered or absorbed along the way, but most traveled freely, carried forward by the expansion of space itself. When they finally reach Earth, they arrive almost unchanged in direction, carrying with them the conditions of the universe at the moment they last interacted with matter. This is why the cosmic microwave background appears to come from a spherical shell around us. In every direction we look, we see light that has traveled for the same amount of time. We are not at the center of the universe. We are at the center of our observable horizon. Every observer, anywhere in the universe, would see the same thing. This universality is deeply calming. It tells us that the laws of physics operated the same way everywhere, that the early universe was not chaotic or uneven on large scales, but remarkably consistent. The tiny irregularities we see are not flaws, they are features. Without them, there would be no galaxies. If the cosmic microwave background were perfectly uniform, gravity would have had nothing to work with, matter would remain evenly spread, and the universe would be a thin, featureless fog of atoms. The fact that we exist at all depends on those faint patterns frozen into ancient light. Observing the first atoms, then, is not like looking at an object in space. It is like reading a memory. Telescopes designed to study the cosmic microwave background do not take pictures in the usual sense. They measure temperature differences across the sky with extraordinary precision. Satellites like COBE, WMAP, and Planck have mapped this light in increasing detail, revealing a universe that is both simple and subtle. The results are astonishingly precise. From these measurements, scientists have determined the age of the universe to within a few tens of millions of years. They have measured the proportions of ordinary matter, dark matter, and dark energy. They have confirmed that space is nearly flat on large scales. All of this comes from light released when the first atoms formed. Even more remarkable is how well these observations match theoretical predictions. Equations developed decades earlier predicted the existence of this background radiation, its temperature, and its basic structure. When it was finally detected, it confirmed a deep understanding of cosmic history. The first atoms left an imprint not because they were special individually, but because they changed how the universe behaved as a whole. By becoming neutral, atoms allowed light to escape. By allowing light to escape, they preserved a snapshot of the universe's state. By preserving that snapshot, they made observation possible. This chain of cause and effect stretches across billions of years, linking the quiet formation of hydrogen atoms to the sophisticated instruments we use today. As you lie here now, it can be soothing to remember that the universe has been telling its story continuously, without interruption. The light we observe today is not new. It is ancient, patient, and honest. It has crossed expanding space without losing its message. In a very real sense, you are surrounded by the afterglow of creation. not in a dramatic way, but in a gentle one. A uniform whisper filling the cosmos, reminding us that stability, once achieved, can endure. And as we continue this calm journey forward through time, another question naturally emerges. If the first atoms left such a lasting imprint, how did gravity take those faint density patterns and turn them into the towering structures of galaxies and clusters we see today? Part 9. Why hydrogen mattered more than anything else. Hydrogen may seem unremarkable, but it became the foundation of everything that followed. Nearly all ordinary matter in the universe began this way. Hydrogen clouds gathered under gravity, slowly thickening, slowly compressing. Without hydrogen stability, there would be no stars, no heavier elements, no chemistry complex enough to build planets, oceans, or life. Hydrogen's importance lies not in what it is, but in what it allows. It is the simplest atom possible, yet that simplicity makes it extraordinarily flexible. With just one proton and one electron, hydrogen is easy to form, easy to move, and easy for gravity to gather. In a young universe still learning how to hold itself together, those qualities mattered more than complexity ever could. After recombination, the cosmos was filled almost entirely with hydrogen atoms drifting through expanding space. Helium existed too, formed earlier in the first few minutes of nuclear fusion, but hydrogen dominated by sheer number. More than 9 out of every 10 atoms were hydrogen, and for a long time, that was almost all there was. This abundance was not an accident. The early universe cooled too quickly for heavier elements to form. Nuclear reactions that could build carbon, oxygen, or iron require sustained heat and pressure, conditions that would not exist until stars formed much later. Hydrogen, by contrast, could exist under gentle conditions. It did not require violence to be born. It simply required calm. Hydrogen also interacts with gravity in a uniquely useful way. Because hydrogen atoms are light, they respond readily to even weak gravitational pulls. In the early universe, density differences were tiny, so small they are barely visible in the cosmic microwave background. But over millions of years, gravity amplified those differences. Regions that were slightly denser attracted more hydrogen. As more hydrogen gathered, gravity strengthened, pulling in still more. This process was slow, quiet, and relentless. Hydrogen clouds grew larger and heavier, stretching across tens, then hundreds, then thousands of light years. Within these clouds, temperatures rose slightly as atoms collided more frequently. Pressure increased. The balance between gravity pulling inward and heat pushing outward shifted gradually. Eventually, in the densest regions, gravity won. Hydrogen clouds collapsed. As they collapsed, temperatures climbed dramatically. At their centers, hydrogen atoms were compressed so tightly that electrons were stripped away again, forming a hot plasma. When temperatures reached millions of degrees, something extraordinary happened. Hydrogen nuclei began to fuse. The first stars ignited. This is where hydrogen's second great role begins. Not only is hydrogen the most common atom, it is also the fuel of stars. Through nuclear fusion, hydrogen powers stellar light and heat, sometimes for billions of years. In the core of a star, hydrogen nuclei combine to form helium, releasing energy according to Einstein's equation, E equals mc squared. That energy pushes outward, balancing gravity's cataclysmic inward pull. It is this balance that allows stars to shine steadily rather than collapsing or exploding immediately. Every star you have ever seen is, at heart, a machine for turning hydrogen into something else, and it does not stop there. Inside stars, hydrogen fusion creates helium. In more massive stars, helium can fuse into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon, and eventually iron. Each step builds complexity from hydrogen's simple beginning, but iron marks a limit. Fusion beyond iron does not release energy, it consumes it. When a massive star fills its core with iron, it can no longer support itself. Gravity takes over and the star collapses, often exploding as a supernova. In that explosion, elements heavier than iron are created and scattered into space. Gold, uranium, iodine, and many other elements essential to planets and biology owe their existence to stars that began as hydrogen clouds. Without hydrogen, there would be no stellar furnaces to build the periodic table. Hydrogen also shaped the structure of the universe on the largest scales. Vast filaments of hydrogen trace the cosmic web, outlining the distribution of galaxies across billions of light years. Even today, much of the universe's hydrogen remains between galaxies, forming enormous reservoirs of gas that slowly feed star formation over cosmic time. Astronomers detect this hydrogen through its characteristic signals, such as the 21-centimeter emission line. This faint radio signal allows scientists to map hydrogen across the universe, revealing structures that would otherwise be invisible. In this way, hydrogen is both ancient and present. It is the universe's most enduring ingredient. Hydrogen also plays a quiet but crucial role in chemistry. When stars die and spread heavier elements into space, hydrogen combines with them to form molecules. Water, the foundation of life as we know it, is hydrogen bonded to oxygen. Organic molecules rely on hydrogen bonds to hold complex structures together. Even the chemistry inside your body depends on hydrogen's behavior. Hydrogen bonds shape the structure of DNA. They allow proteins to fold. They enable water to have its unique properties, such as high heat capacity and surface tension. These subtle effects trace back to the simplest atom formed in the early universe. In this sense, hydrogen is not just a cosmic building block, it is an enabler of complexity. What makes this especially striking is how unassuming hydrogen is. It has no internal layers beyond a single proton, no heavy nucleus, no elaborate electron structure, and yet its very simplicity allows it to participate in almost every important process in the universe. Complexity did not need a complex beginning. It needed a stable one. Hydrogen provided that stability. It was abundant enough to matter, simple enough to form easily, and versatile enough to fuel stars and chemistry alike. Other atoms could only appear later, built upon hydrogen's quiet foundation. There is also a philosophical calm in this realization. The universe did not rush toward complexity. It did not begin with richness. It began with something small, uniform, and patient. Hydrogen drifted for millions of years before the first star ever lit up. Nothing dramatic happened for a very long time, yet all the potential was already there. As you rest now, surrounded by complexity, electronics, architecture, biology, it can be grounding to remember that everything traces back to hydrogen. The atoms in your body were once part of those early clouds. They drifted through darkness long before Earth existed, long before the sun formed. Hydrogen waited, and in waiting, it made everything else possible. As we continue this gentle journey through cosmic history, one question naturally follows. If hydrogen laid the foundation for stars and elements, how did gravity organize this simple matter into the vast galaxies and structures we see stretching across the universe today? Part 10. How gravity began shaping structure after atoms formed. Once atoms existed, gravity finally had something to work with. Neutral matter could clump without being torn apart by radiation pressure. Over millions of years, regions slightly denser than their surroundings began to grow. These gentle imbalances were enough. Gravity amplified them patiently, drawing matter inward, laying the groundwork for stars and galaxies yet to come. Before atoms formed, gravity had been present but restrained. Radiation dominated the universe's behavior. Photons carried so much energy that they constantly pushed against matter, smoothing out any attempt at collapse. Density differences struggled to survive. Matter wanted to gather, but light would not let it. Recombination changed that balance. When electrons bound to nuclei and light decoupled from matter, radiation pressure weakened dramatically. Photons streamed freely through space instead of bouncing endlessly off charged particles. Matter was left to follow gravity's quiet pull with far less interference. This shift did not create structure instantly. Gravity is not a force of speed. It works slowly, accumulating small effects over long spans of time. But once atoms existed, gravity could finally begin its true work. The universe at this stage was still remarkably uniform. The density variations visible in the cosmic microwave background were tiny. differences of just 1 part in 100,000. To human intuition, these seem insignificant. To gravity, they were everything. Where matter was slightly denser, gravity was slightly stronger. That tiny advantage mattered. Over time, denser regions pulled in more atoms from their surroundings. As more matter gathered, gravity increased, strengthening the pull further. This positive feedback loop is the essence of gravitational growth. The process was gentle. There were no collisions at first, no sudden bursts. Hydrogen atoms drifted slowly, guided by gradients in density and the faint tug of gravity. The universe remained dark, quiet, and cold. This long era is often called the cosmic dark ages. Darkness here means the absence of stars, not the absence of activity. Matter was moving, clouds were forming, structure was emerging invisibly, like roots growing underground before a forest appears. An important companion to ordinary matter was already shaping this process: dark matter. Dark matter does not interact with light at all. It neither emits nor absorbs radiation. It had decoupled from light far earlier than ordinary matter, allowing it to begin clumping even before atoms formed. By the time recombination occurred, dark matter had already laid down a scaffolding of gravitational wells across the universe. Ordinary matter followed. Hydrogen atoms fell into these dark matter structures, deepening them further. The interplay between visible matter and invisible dark matter defined the large-scale structure of the cosmos. This is why galaxies form where they do. They are not random collections of stars, they are the luminous centers of much larger dark matter halos, regions where gravity gathered matter over hundreds of millions of years. As hydrogen accumulated in these halos, clouds grew denser. Collisions between atoms became more frequent. Temperature rose slightly in the densest regions, though space overall continued to cool as the universe expanded. Eventually, in the cores of the densest clouds, gravity overcame pressure completely. Collapse accelerated. As matter fell inward, gravitational potential energy converted into heat. Temperatures climbed rapidly. At the center of these collapsing clouds, conditions became extreme enough to ignite nuclear fusion. The first stars were born. But that moment lay far in the future. For tens of millions of years after atoms formed, gravity worked in near silence, shaping structure without light, without spectacle. This slowness is important. If gravity had acted too quickly, matter might have collapsed into black holes before stars could form. If it had been too weak, matter might never have gathered enough to ignite fusion. The universe again found itself in a narrow, balanced window. Structure formation depends on this balance. Gravity pulled inward, thermal motion resisted collapse, radiation pressure had faded, but it had not vanished entirely. The competition between these influences determined where and when stars would form. The earliest structures were small by modern standards, proto-galaxies containing perhaps millions of solar masses of gas. Over time, these merged and grew, forming larger galaxies and clusters. This hierarchical growth continues even today. Galaxies collide, clusters assemble. Gravity never stops working. It only slows as expansion stretches space further apart. It is also worth noting that gravity does not create order directly. It amplifies what already exists. The initial density fluctuations, tiny as they were, determined the universe's large-scale pattern. Gravity traced those faint lines and made them visible. In this sense, the structure of the universe is a memory of its earliest moments. The filaments of galaxies we observe today mirror the faint ripples frozen into the cosmic microwave background. The universe's present shape echoes its past. From a human perspective, gravity feels powerful and immediate. We feel its pull every moment. On cosmic scales, gravity feels different. It is slow, patient, almost meditative. It does not rush, it waits. Hydrogen atoms drifting in space had no awareness of their future. They followed simple rules, responding to forces without intention. And yet, from this mindless motion emerged stars, galaxies, planets, and eventually observers capable of wondering how it all began. This is one of the quiet wonders of cosmology. Complexity arises not from intricate rules, but from simple ones applied over vast spans of time. Gravity, in its simplicity, reshaped the universe once atoms allowed it to act freely. It turned a nearly uniform fog of hydrogen into a richly structured cosmos. As you rest now, held gently to Earth by gravity's constant pull, it can be calming to remember that this same force shaped the largest structures in existence. The gravity that keeps you grounded also gathered the atoms that became stars. Nothing about this process was violent at first. It was subtle, cumulative, patient. Only much later would gravity unleash more dramatic events, supernovae, black hole mergers, and bursts of energy powerful enough to be seen across the universe. For now, in this chapter of cosmic history, gravity worked quietly, laying foundations without spectacle. And as we continue this slow journey forward through time, another question naturally arises. Once gravity built the first stars, how did those stars begin transforming the universe again, ending the long darkness and setting the stage for the most powerful explosions since the Big Bang? Part 11. Why the first atom didn't create stars immediately. Nothing in the universe happens quickly at this scale. After the first atoms formed, there was a long, dark age. No stars yet burned. Space was filled with cold hydrogen, drifting silently. This quiet period lasted hundreds of millions of years. It was not emptiness, but preparation. The universe was gathering itself. It can be tempting to imagine the first atom as a spark, something that should immediately ignite activity. But atoms alone are not enough to create stars. Stars require patience, mass, and time. And in the early universe, all three were still slowly assembling. After recombination, the universe entered what cosmologists call the cosmic dark ages. Darkness here does not mean absence of matter or motion, it means absence of light sources. There were no stars, no galaxies, no glowing objects at all. The only light present was the fading afterglow of the Big Bang itself, steadily, redshifting into microwaves as space expanded. Hydrogen atoms filled the universe almost uniformly. They were neutral, cold, and widely spaced. Gravity was working, but gently. The density variations that existed were tiny. From one region to another, the difference in matter content was almost imperceptible. For gravity to turn atoms into stars, matter must clump dramatically. Temperatures must rise. Pressure must increase until nuclear fusion becomes possible. None of that could happen quickly in such a smooth, expanding cosmos. Expansion itself was part of the delay. As the universe grew larger, distances between atoms increased. Even as gravity tried to pull matter together, expansion worked in the opposite direction, stretching space and thinning matter out. Gravity had to overcome not only thermal motion, but the expansion of the universe itself. This made collapse slow. In the densest regions, gravity gained a small advantage. Hydrogen atoms drifted inward, collecting gradually. But the process took tens, then hundreds of millions of years. There were no sudden infalls, no dramatic implosions, just steady accumulation. Cooling was another challenge. For a cloud of gas to collapse into a star, it must lose heat. As gas compresses, it warms. If that heat cannot escape, pressure builds and collapse halts. In the early universe, hydrogen clouds had limited ways to shed heat. There were no heavier elements yet to radiate energy efficiently. No dust, no complex molecules. Pure hydrogen is a poor coolant. This meant that even when hydrogen clouds grew massive, they struggled to collapse fully. Heat slowed them down, forcing gravity to work even longer to bring temperatures and densities to stellar ignition levels. Dark matter played a crucial role during this time. Long before atoms formed, dark matter had already begun clumping. It does not interact with light or radiation, so it was free to gather early. By the time of recombination, dark matter had formed a network of gravitational wells across the universe. Hydrogen atoms fell into these wells. But falling into a dark matter halo does not automatically create a star. It simply creates a reservoir of gas. That gas still needed time to cool, compress, and fragment. This is why the first stars formed relatively late, around 100 to 200 million years after the Big Bang. From a human perspective, that is an eternity. From a cosmic perspective, it is still the opening act. The first stars, known as population 3 stars, were unlike any stars that exist today. They formed from almost pure hydrogen and helium with no heavier elements at all. Because of this, they behaved differently. They grew very large, burned very hot, and lived very short lives. But before they could exist, the universe had to wait. This waiting period is essential to understand because it highlights a deep truth about cosmic evolution. Complexity is not rushed. The universe does not jump from simplicity to richness in a single step. It builds gradually, allowing each stage to settle before the next begins. The first atom created stability. But stability alone does not produce light. Gravity needed time to gather enough matter, gas needed time to cool, dark matter needed time to deepen its wells. All of this happened quietly, invisibly, in the dark. During this era, the universe was not empty. It was full of motion too subtle to glow. Hydrogen clouds stretched across vast regions of space. Some grew denser than others. Small proto-galaxies began to form, though they were still dark. Matter streamed along filaments, guided by gravity's invisible architecture. The universe was already structured before it ever lit up. This is another important point. Light does not create structure, it reveals it. By the time the first stars ignited, much of the universe's large-scale pattern was already in place. Stars were not the beginning of order. They were the first visible expression of an order that had been quietly forming for hundreds of millions of years. From within this darkness, the conditions for ignition slowly matured. In the densest pockets of gas where gravity had gathered hydrogen more effectively, collapse finally accelerated. Temperatures climbed into the millions of degrees. Electrons were stripped from nuclei again, forming hot plasma. And at the very center, hydrogen nuclei began to fuse. The first stars turned on. But their arrival does not diminish the importance of the long wait that preceded them. Without that patient preparation, stars could not exist at all. The universe needed time to arrange itself into a state where fusion was possible. There is something deeply calming about this slowness. The cosmos is not frantic. It does not rush toward outcomes. It allows processes to unfold at their natural pace, governed by simple laws applied over immense spans of time. As you rest now, it can be reassuring to remember that even the most luminous objects in the universe were born from long periods of darkness and quiet accumulation. Nothing important was wasted in that silence. The cosmic dark ages were not a void. They were a gestation period. A time when gravity rehearsed its role, when matter learned how to gather, when the universe practiced patience. And when the first stars finally ignited, they did so atop foundations laid slowly, carefully, without haste. As we continue this gentle journey forward, another question begins to glow ahead. When those first stars finally turned on, how did they transform the universe again? And why did their light mark the end of darkness and the beginning of the most powerful explosions since the Big Bang? Part 12. How the first atoms led to the first stars. Eventually, gravity won its slow contest. Hydrogen clouds collapsed until their cores grew hot enough to ignite nuclear fusion. The first stars were born, massive and short-lived, forging heavier elements in their cores. But none of that could happen without the earlier moment when electrons and protons first agreed to stay together. The path from the first atom to the first star was long, quiet, and indirect. There was no straight line between them. Instead, there was patience. Hydrogen atoms drifted for millions of years, responding to gravity so gently that, from any local point of view, almost nothing seemed to be happening at all. Yet, gravity never stopped working. Once atoms existed, matter could cool more effectively than plasma ever could. Neutral hydrogen no longer scattered light constantly, and with fewer interactions, the universe grew calmer. In this calmer environment, gravity's influence became more pronounced, not stronger in force, but freer in expression. Tiny density variations, so small they are barely visible in the cosmic microwave background, began to matter. Where hydrogen was slightly more concentrated, gravity pulled a little harder. That small advantage compounded over time. Atoms drifted inward, clouds grew thicker. The difference between dense and less dense regions slowly sharpened. This process was not uniform. Most hydrogen remained diffuse for a very long time, spread thin across expanding space. But in certain regions, guided by the gravitational scaffolding of dark matter, gas accumulated more efficiently. These regions became the cradles of the first stars. As hydrogen gathered, something subtle but important happened. Collisions between atoms became more frequent. With each collision, kinetic energy turned into heat. Temperatures inside the densest clouds began to rise, not dramatically at first, but steadily. At the same time, pressure increased. This introduced a delicate balance. Gravity pulled inward, thermal pressure pushed outward. For collapse to continue, gravity had to win. That required mass. Only clouds above a certain size could overcome their own internal heat and continue collapsing. In the early universe, this threshold was high. With no heavier elements to help radiate heat away, cooling was inefficient. Hydrogen and helium alone do not shed energy easily. This meant that the first collapsing clouds had to be enormous, far larger than the clouds that form stars today. When collapse finally accelerated, it did so decisively. Gas streamed inward, densities climbed, temperatures soared. At the very center of these collapsing clouds, conditions became extreme. Electrons were stripped from nuclei again, forming a hot plasma. Pressure rose, but gravity pressed harder still. Eventually, the core temperature reached tens of millions of degrees. At that point, nuclear fusion began. Hydrogen nuclei, protons, started to combine, forming helium and releasing energy in the process. This release of energy was not destructive, it was stabilizing. The outward pressure from fusion balanced the inward pull of gravity, halting collapse. A star had formed. The first stars were unlike most stars we see today. They formed in a universe with no metals, no elements, heavier than helium. This absence changed everything about their behavior. These early stars, known as population 3 stars, grew extraordinarily massive. Some may have reached hundreds of times the mass of the Sun. Their size made them luminous and hot, burning through their hydrogen fuel at a furious pace. They lived fast. Instead of shining for billions of years like our Sun, many of these first stars lived for only a few million years. In cosmic terms, that is a brief flicker. But in that short time, they transformed the universe. Inside their cores, fusion continued beyond hydrogen. Helium fused into carbon, carbon into oxygen. Heavier elements began to appear for the first time since the earliest minutes of the universe. These stars became the universe's first factories of complexity. When the most massive of these stars died, they did not fade quietly. They collapsed and exploded, scattering newly forged elements into surrounding space. Supernovae lit up the dark universe, briefly outshining entire galaxies that had not yet fully formed. These explosions marked the beginning of chemical diversity. The heavy elements released by the first stars mixed with surrounding hydrogen, enriching future generations of gas clouds. With these new elements came new possibilities. Gas could cool more efficiently. Clouds could fragment into smaller pieces. Stars could form with lower masses and longer lifespans. The universe learned how to build variety. But it all traces back to atoms. Without the first stable hydrogen atoms, none of this could happen. No clouds could persist, no cooling could occur, no gravity-driven collapse could proceed to completion. The first atom did not shine, but it made shining possible. It is also worth noting how delayed this process was. Hundreds of millions of years passed between the formation of atoms and the ignition of the first stars. This delay is not a flaw in the story, it is the story. The universe required time to prepare. Gravity needed time to gather matter. Gas needed time to cool. Dark matter needed time to shape the landscape. The first stars were not spontaneous, they were earned. When they finally appeared, they did more than light up the darkness. They changed the universe's chemistry, its temperature, and its future direction. Their radiation began to reionize surrounding hydrogen, altering the state of the intergalactic medium once again. In this way, the universe entered a new phase. The calm neutrality established at recombination did not last forever. The first stars reintroduced ionization locally, carving out bubbles of hot, glowing plasma in the surrounding gas. Over time, these bubbles grew and overlapped, ending the cosmic dark ages. Light returned, but now in concentrated points rather than a uniform glow. From then on, the universe became a place of contrast. Bright stars against dark space, galaxies surrounded by vast voids. Complexity accelerated, planets formed, life became possible. All of this followed from a single quiet agreement between an electron and a proton. That agreement allowed atoms to exist. Atoms allowed clouds. Clouds allowed stars. Stars allowed everything else. As you rest now, beneath a sky filled with starlight, it can be grounding to remember how indirect this journey was. Nothing was rushed. Nothing was wasted. The universe took its time. The first stars were not a beginning, but a continuation, a visible expression of processes set in motion hundreds of millions of years earlier. And as we continue this calm exploration, another question naturally unfolds. Once stars began to live and die, forging heavier elements and releasing immense energy, how did these processes lead to the most powerful explosions the universe has seen since its birth? Part 13. Why complexity begins with simplicity. The universe did not start with variety, it started with repetition. Hydrogen atoms again and again filling space. From that sameness emerged everything else. Complexity was not imposed from the start. It unfolded gradually, built layer by layer upon a foundation of stability, patience, and time. At first glance, simplicity can feel limiting. One atom, one pattern, one repeated structure across unimaginable distances. But in the universe, simplicity is not a lack of possibility. It is the condition that allows possibility to grow. In the earliest eras, the universe had no room for complexity. Energy was too intense. Motion was too constant. Anything intricate would have been torn apart almost instantly. Stability had to come first. Hydrogen provided that stability, not because it was rich or varied, but because it was resilient. A hydrogen atom is minimal. One proton, one electron, nothing extra. And because there is so little to disrupt, it is remarkably durable once conditions allow it to exist. This durability is what made the next steps possible. When the universe cooled enough for hydrogen to persist, it did not immediately become interesting in the way we think of interest. It became repetitive, uniform, predictable. The same atom replicated trillions upon trillions of times, drifting quietly through space. This repetition mattered. With repetition comes reliability. With reliability comes accumulation. When every building block behaves the same way, large-scale patterns can emerge. Gravity can work consistently. Interactions can compound. Small differences can be amplified. If the early universe had been chemically complex from the start, its behavior might have been chaotic in a different way. Too many reactions, too many pathways, too much variation too soon. Instead, the universe began with a clean slate, allowing complexity to arise naturally rather than being forced. Hydrogen's sameness made it predictable. Predictability allowed gravity to sculpt matter into structures without surprises. Clouds formed, collapses occurred, stars ignited, each step built upon the last, not by replacing simplicity, but by layering complexity on top of it. This layering is essential. Complex systems rarely emerge all at once. They grow by stacking simple rules over time. In physics, this is a recurring theme. From simple equations come elaborate behaviors. From basic forces arise intricate forms. The universe followed this pattern faithfully. First came particles, then atoms, then clouds, then stars, then galaxies. Each stage relied on the stability of the previous one. None of them skipped ahead. Even stars, which feel dramatic and complex to us, operate on simple principles. Gravity pulls inward, fusion pushes outward, balance determines lifespan. Inside that balance, however, complexity flourishes. Different fusion pathways create different elements. Different masses create different stellar fates. From hydrogen's simplicity came stellar diversity. As stars lived and died, they introduced variation. Supernovae scattered heavier elements into space. Gas clouds enriched with carbon oxygen, silicon, and iron behaved differently than pure hydrogen clouds. Cooling became more efficient, fragmentation became easier. Smaller stars could form. Complexity accelerated, but it never abandoned its simple roots. Even today, hydrogen remains the most abundant element in the universe. It fuels stars, it fills interstellar space, it binds with other elements to form molecules essential to life. Complexity does not replace simplicity. It coexists with it. There's a quiet lesson here. The universe did not seek complexity for its own sake. It allowed complexity to emerge as a consequence of stability and time. There was no rush to variety. There was no need to begin with richness. Instead, richness was earned through repetition and patience. This is why the early universe feels so calm in hindsight. It was not trying to do too much at once. It allowed one thing to happen fully before the next began. From a human perspective, this can feel almost comforting. We often associate progress with speed, with rapid change, with constant novelty. The universe suggests another path, one where repetition builds strength, where simplicity lays the groundwork for depth. Hydrogen atoms drifting through darkness may not seem like much, but given time, they became stars. Given stars, they became elements. Given elements, they became planets. Given planets, they became chemistry. Given chemistry, they became life. At no point did the universe need to abandon its early simplicity. It simply added to it. Even the most complex structures we know, cells, brains, ecosystems, are built from simple units repeating patterns over and over. Complexity is not the opposite of simplicity. It is simplicity arranged over time. The early universe demonstrates this principle on the largest possible scale. There is also humility in this story. Nothing about the universe's beginning suggests intention toward complexity. There was no goal of life, no plan for consciousness, and yet, by following consistent rules patiently, the universe created conditions where complexity could arise naturally. This does not diminish wonder. It deepens it. As you rest now, surrounded by a world of staggering intricacy, it can be soothing to remember that everything traces back to repetition, to atoms behaving the same way, again and again, without deviation. Your body is made of atoms forged in stars that began as hydrogen clouds. Your thoughts arise from neurons firing according to simple electrical rules. Complexity surrounds you, but it rests on foundations that are calm, stable, and ancient. The universe did not begin with variety because it did not need to. It began with consistency. And in that consistency, given enough time, everything else emerged. As we continue this gentle journey toward the later, more violent chapters of cosmic history, another question quietly waits ahead. When complexity finally matured, how did it give rise to forces powerful enough to unleash explosions rivaling the energy of the early universe itself? Part 14. What the first atom teaches us about existence. The first atom reminds us that profound change does not require drama. Sometimes it only requires conditions to become gentle enough. The universe did not force matter into existence. It waited until matter was ready. In that waiting, everything you know was made possible. It is easy to imagine the universe's most important moments as loud ones, explosions, collisions, bursts of light. We tend to associate significance with violence, with suddenness, with events that announce themselves unmistakably. But the first atom formed without spectacle. No flash marked its arrival. No wave of energy rolled across space. One electron simply remained where it had always been drawn, and for the first time, it was not torn away. That quiet success changed the universe more deeply than any explosion that followed. Before atoms, the universe was restless. Energy dominated. Nothing could hold. Everything was temporary. Motion erased memory as quickly as it created it. In such a universe, nothing could accumulate. Nothing could build upon what came before. The first atom introduced endurance. It showed that the universe could sustain something stable, that bonds could last, that patterns could persist longer than an instant. From that moment on, the universe was no longer only a place of becoming. It became a place of keeping. This teaches us something subtle about existence itself. Stability is not the opposite of change. It is the condition that allows meaningful change to occur. Without stability, everything resets. With stability, history begins. The universe did not rush to this point. It expanded, it cooled, it waited. Hundreds of thousands of years passed before atoms could exist. From a human perspective, that seems unimaginably slow. From a cosmic perspective, it was simply necessary. The laws of physics did not bend to make atoms happen sooner. They remained consistent, allowing conditions to evolve naturally until stability was possible. There is a kind of quiet integrity in that process. Nothing was forced. This patience is written into everything that followed. Stars did not appear immediately after atoms. Planets did not appear immediately after stars. Life did not appear immediately after planets. At each stage, the universe paused, not in stillness, but in preparation. The first atom is a reminder that readiness matters. Connection cannot occur when energy is too high. Bonds cannot form in chaos. Complexity cannot arise in constant turbulence. The universe teaches us that conditions must soften before structure can emerge. There is also humility in the first atom's simplicity. Hydrogen is not impressive by itself. It has no color, no complexity, no variety. And yet, it became the foundation of everything else. This suggests that importance is not always found in richness or detail. Sometimes it is found in reliability. The first atom did not do much. It simply stayed together. That was enough. From that simple act of staying came stars, galaxies, chemistry, biology, and consciousness. None of those things were present in the atom itself. They emerged later, layered slowly on top of that original stability. Existence, it seems, is cumulative. This has philosophical weight. It suggests that the universe values persistence over intensity, continuity over immediacy. A system that allows things to remain can eventually allow things to grow. Even the most dramatic events in cosmic history, supernovae, black hole mergers, gamma-ray bursts, depend on long periods of quiet stability beforehand. A star must burn steadily for millions of years before it can explode. A galaxy must assemble patiently before it can host violence on a grand scale. The loud moments are built on silent ones. The first atom also teaches us about fragility. That bond between electron and proton is not strong in an absolute sense. It can be broken by enough energy. It was broken constantly in the early universe. Even today, atoms can be ionized under extreme conditions. Stability is conditional. It exists only within a certain range of environments. Too much heat and bonds break. Too little motion and reactions cease. The universe exists in a delicate balance between extremes. Your own existence rests within such a balance. The temperature of your surroundings, the strength of chemical bonds, the behavior of molecules in your body, all depend on conditions being neither too violent nor too inert. This balance traces directly back to the universe's ability to cool enough for atoms to exist. In that sense, the first atom is not just a historical event, it is an ongoing requirement. Every moment you exist is a continuation of that ancient cooling. There is also comfort in knowing that the universe did not begin with complexity and then decay into simplicity. It began with simplicity and grew more intricate over time. This direction matters. It suggests that complexity is not a fluke, but a natural outcome when simple rules are allowed to operate patiently. The universe did not need special instructions to produce richness. It needed time. Time itself changed meaning with the first atom. Before stability, time was difficult to define. Everything happened too quickly, too uniformly, too chaotically. After atoms formed, processes could unfold at different rates. Some things changed quickly, others slowly. A sense of before and after gained substance. History became possible. The first atom marks the beginning of a universe that could remember itself. The cosmic microwave background preserves that memory. The distribution of galaxies preserves it. The elements in your body preserve it. Existence is not just about being present, it is about carrying forward what has been. The first atom carried forward a moment of calm in an otherwise restless universe. That calm propagated across billions of years, enabling everything that followed. As you rest now, breathing quietly, it may feel strange to connect your stillness to an event so distant, but the connection is real. The same physics that allowed the first atom to remain intact allows your body to exist in its current form. You are made of ancient agreements between particles that learned long ago how to stay together. There is no urgency in that realization, no demand, just perspective. The universe did not hurry you into existence. It prepared for you slowly, without knowing you would ever arrive. And yet, here you are, the result of a chain of stability stretching back to the first moment matter could endure. The first atom teaches us that waiting is not absence, it is readiness. That gentleness is not weakness, it is a prerequisite for creation. And as we approach the final chapter of this journey, one last question quietly settles in. After all this patience, all this calm preparation, how did the universe eventually produce moments so violent that they rival the energy of its own beginning? Part 15. Why this moment still matters to you. Every atom in your body traces its history back to that first successful bond. The calm arrangement of electrons around nuclei is not just ancient physics. It is happening inside you right now, holding you together quietly, reliably. The first atom was not just the beginning of matter, it was the beginning of continuity. And that continuity has never been broken. It can be easy to think of the early universe as something distant, sealed off from your daily life by billions of years and unimaginable scales. But the truth is softer than that. The physics that allowed the first atom to exist is the same physics that allows you to exist now. Nothing fundamental has changed since that moment. The rules have remained consistent. The universe has simply been unfolding their consequences ever since. Right now, as you breathe, electrons remain bound to nuclei throughout your body. They do not wander off. They do not collapse inward. They occupy stable arrangements defined by the same electromagnetic forces that first allowed hydrogen to exist. Your bones, your blood, your thoughts, all depend on that same balance between attraction and motion. This is continuity. The universe did not reset after the first atom formed. It did not reinvent itself at each stage. It carried forward what worked. The stability discovered then became the baseline upon which everything else was built. Stars formed without breaking atomic bonds. Planets assembled from atoms already stable. Life emerged by rearranging atoms, not by changing their fundamental nature. You are not separate from that story. You are one of its latest chapters. Every heavier element in your body, carbon, oxygen, calcium, iron, was built from hydrogen in the cores of stars. Those stars could only exist because hydrogen atoms were stable. And hydrogen atoms could only exist because the universe once cooled enough to allow electrons and protons to remain together. Nothing about you escapes that chain. This can be grounding in a quiet way. It means that your existence is not fragile in the sense of being arbitrary. It rests on physical laws that have been tested continuously for nearly 14 billion years. The same forces that held the first atom together have held trillions of atoms together ever since. That kind of reliability is rare. When life feels uncertain, when thoughts feel scattered, it can be calming to remember that at the deepest level, you are composed of systems that know how to stay together. Stability is not something you have to invent. It is built into the universe you inhabit. The first atom also reminds us that beginnings do not need to be dramatic to be meaningful. There was no audience for that first bond, no observer to witness it, and yet its consequences reach all the way to this moment. Meaning, it seems, does not depend on recognition. The universe did not know it was beginning something important. It simply followed its laws as conditions allowed. And from that quiet obedience to physics, everything else emerged. This has implications beyond cosmology. It suggests that continuity, small, reliable persistence, is often more powerful than sudden change. That what lasts tends to shape the future more than what flashes brightly and disappears. The universe itself is an example of this principle. Even the most violent events we study today, supernovae, gamma-ray bursts, black hole mergers, are temporary. They release enormous energy, then fade. What remains afterward are atoms, rearranged but still intact, still obeying the same rules. The first atom outlasts every explosion. In that sense, continuity is the universe's deepest achievement. As you lie here now, your body is a complex arrangement of atoms exchanging energy, information, and motion. But beneath that complexity is something remarkably simple. Particles staying, where they are allowed to stay. Bonds holding. Structures persisting long enough to matter. You do not need to feel this happening for it to be real. It is happening whether you notice it or not, just as it has since the universe was young. There is also a kind of quiet equality in this story. The same atomic rules apply everywhere. In the most distant galaxy and in the smallest cell within you, electrons behave the same way. Protons carry the same charge. Forces act with the same strengths. The universe does not play favorites. This universality connects you to everything else. The atoms in your body were once part of stars that exploded long before Earth existed. Before that, they were hydrogen, drifting through darkness. Before that, they were part of the first atoms that formed when the universe finally became calm enough. You are not borrowing these atoms temporarily. You are part of their long journey. When you exhale, atoms leave your body and rejoin the environment. When you inhale, others take their place. Continuity does not mean stasis, it means persistence through change. The first atom did not freeze the universe into a single form. It allowed transformation to happen without destruction. This is an important distinction. Change that destroys stability resets everything. Change that preserves stability allows growth. The universe chose the second path. That choice echoes in biology, in ecosystems, in civilizations. Systems that preserve their core structures while allowing variation tend to endure. Systems that collapse under their own intensity do not. The first atom is an early example of this wisdom, written into physics rather than philosophy. And perhaps most gently of all, this moment reminds us that existence is not loud by default. It is quiet, sustained, ongoing. The most important processes happen without announcement. You are held together not by effort but by balance. As you rest now, supported by a planet assembled from atoms that have survived cosmic history, it can be comforting to know that you are not an interruption in the universe's story. You are a continuation of it. The continuity that began with the first atom has passed through stars, galaxies, and worlds to arrive here, in this moment of stillness. Nothing needs to be proven. Nothing needs to be rushed. The universe has been practicing patience for billions of years, and you are part of the result. As this journey gently comes to rest, remember this. Long before there were explosions bright enough to terrify scientists, long before there were stars or galaxies at all, there was a moment of calm where matter learned how to stay. That lesson has never been forgotten, and neither have you. As we come to the end of this quiet journey, it's worth resting for a moment in the scale of what we've explored. From a universe too hot for matter to exist, to the first fragile atom, to the slow emergence of stars, structure, and light, everything unfolded not through haste, but through patience. The cosmos did not rush itself into complexity. It allowed stability to arrive first and trusted time to do the rest. The explosions that still capture our awe today, the brightest bursts of energy since the Big Bang, are built on foundations laid in silence. They depend on atoms that learned how to stay together, on stars that burned steadily before they ever died violently, on laws of physics that have remained calm and consistent for nearly 14 billion years. As you rest now, held together by those same quiet rules, you are not separate from this story. You are one of its most recent expressions. The atoms within you have traveled an unimaginable distance through time to arrive here, in this moment of stillness. Thank you for sharing this calm exploration with me. If this journey brought you even a small sense of peace or perspective, I'm deeply grateful you're here. You don't need to do anything else. Just rest, breathe, and let the universe continue its patient unfolding around you. The cosmos is still expanding, the stars are still shining, and the same gentle continuity that began with the first atom is still holding you now. Good night.